Okay, today we're doing a quick discussion of Chebychev's inequality, and then we'll be discussing multiple random variables. But for Chebychev's inequality gets used to prove a couple theorems, and it's useful in a couple different cases. One way or another, it pops up on the quals often enough that you should know it. But Chebychev's inequality says basically what you see on the board here, that given any random variable x and any function g, you can show the expected value of g, the probability that g of x greater than or equal to r is going to be less than or equal to the expected value of g of x over r. And to prove that, first of all, just write the expected value of g of x, which by definition is the integral from minus infinity to infinity of g of x times the density function times dx. Well, taking expected value over the entire support is of course larger than taking expected value over only the range where g of x is greater than or equal to r, because now we're just integrating over a subset of the whole thing. And since, by definition, g of x is greater than or equal to r in that particular range, that means that that if we simply substitute r for g of x, then the resulting quantity will still be less than or equal to g of x times f of x. So now we're just integrating in the area where g of x is greater than or equal to r with respect to the original density function, and that, of course, by definition is just r times the probability that g of x is greater than or equal to r, which is what we were trying to show. So, simple application of Chebychev's inequality. If you've taken statistics before, you've probably seen the general problem of given some random variable, we know its mean and variance, can we put a bound on the variance? Can we calculate some type of confidence interval for the mean given the variance? Well, if you've taken statistics before, you know, if you're willing to assume normality and a few things like that, then there are some standard tricks for this. Let's say we don't know that it's normal. We don't want to assume that it's normal. We just want to assume that it's some arbitrary distribution. So let's say we write r equals t squared and apply Chebychev's inequality. That gives us the probability that x minus mu squared over sigma squared is greater than or equal to t squared is less than or equal to 1 over t squared times x minus mu expected value of x minus mu squared over sigma squared, which, if we simplify, gives us the probability the absolute value of x minus mu is greater than or equal to t sigma is going to be less than or equal to 1 over t squared. And this is true for any distribution that you can think of, even if it's not normally distributed, that the probability that x is more than t sigma way than mu cannot be more than 1 over t squared, no matter what the distribution of x is. Well, that's not 100% true. I should have added the caveat that for this inequality to hold, maybe it goes without saying, but the expected value of x has to actually exist. If you have like a Cauchy or something like that, where the expected value is infinite, then this will not apply. But if you're willing to take just the very mild condition that the expected value, and in this case the variance, exists, then by Chebychev's inequality this will hold. And another inequality that's specific to the normal distribution, and to me it's more of a curiosity than actually useful these days, given that it was useful in the past when we didn't have computers that could do this, and the only way to calculate values of a normal CDF was from a table or hand computation or something like that. Now that we have R and SAS, there's not really any point other than the fact that this is another sort of thing that they sometimes like to put on qualifying exams. So I'm not going to emphasize it heavily in this class, but it's good to understand the logic just in case you're required to use it again someday. So let's say that you have a variable with the standard normal distribution. Well, hopefully remember, if you want to calculate the probability that this standard normal random variable is greater than or equal to t, that's going to be the integral from t to infinity of 1 over the square root of 2 pi of e to the minus x squared dx, which in that particular range, obviously x divided, if we're integrating from t to infinity, then within that range, x is going to be greater than or equal to t, so x over t is going to be greater than or equal to 1. So that integral is going to be bounded by this integral, and the reason that we use that particular bounding integral is because when we write it in that form, then it actually has a nice antiderivative, and taking the antiderivative, evaluating the limits, blah, 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 we end up with 1 over the square root of 2 pi times e to the minus t squared over 2 divided by t. And if you want to find a bound for the probability that the absolute value of z is greater than or equal to t, i.e. if you get some normal test statistic z and want a bound on the probability of getting something bigger than t, that's just going to be 2 times the probability that we calculated above, or square root of 2 over pi times e to the minus t squared over 2 divided by t. So, I mean, as I said, it's not obvious to me why someone would ever want to use this nowadays, given that we can calculate the exact probability without resorting to bounds in seconds using R, unless it's just somebody trying to write a qualifying exam question having a hard time coming up with something better.
Is there a smaller bound?
Probably, but I mean, once again, like, if given that you can just use Q norm or P norm to get the exact value, I mean, I'm not sure why one would ever care about these sort of bounds in the first place. But, yeah. I mean, it is interesting to know, and I guess if I go back to the previous slide, t equals 2, the bound is 0.054, which is not half bad, given that, as you'll recall, at t equals 1.96, that's almost exactly 0.05 tail probability, so it's pretty close to the actual truth, although, again, given the actual truth is so easily calculated. Any questions about Chebychev's inequality or this other inequality before I go to multiple random variables? Okay, so most of the discussion thus far that we've considered in this class has been focusing on one random variable at a time, but nowadays it's very rare for you to do a study where you only collect one variable of interest, and it's actually kind of a modern thing that there was a famous story that there was a famous paper published in the late 90s by Benjamini and Hochberg talking about how to handle this issue of multiple hypothesis testing when you look at like 100 different genes associated with cancer and want to just say that you find 7 are significant, what's the probability that happened due to chance? Well, when they first submitted this paper in the early 90s, apparently they got a lot of resistance from reviewers saying like, why would anybody ever care about testing like 100 variables at the same time? Nobody ever has more than like 20, 30 variables at once. If you've paid attention to modern statistics at all, you know how laughably wrong that turned out to be. Just taking like genomics examples, for instance, it's quite common If you're looking at gene expression, for instance, you're looking at expression levels of tens of thousands of genes simultaneously. If you're looking at genome-wide association studies, it's common to look at several million genetic markers at once. Genetic studies aside, you can see the examples on here that even like a simple study on cancer, you may want to study survival, quality of life, toxicity, age, gender, race, were they smoking, etc., etc. Just about any study that you ever consider, you're going to be collecting large numbers of variables, and in modern statistics you're not typically going to be interested in only saying something about one variable at a time. You want to know how these variables interact with one another, which means you have to be able to say something about what we call a joint distribution of these variables, how they interact together, not just by themselves. So, starting with the formal definition, that a random variable, given some probability space, sigma, some associated sigma field, A, and a probability measure, P, an n-dimensional random vector is just a function from the sample space omega into Rn. Random variables that we've considered thus far are just a function from omega into R. Now it's to Rn, i.e. it maps to multiple real numbers, not just one. If you're never planning on taking 760, you can probably just take a quick glance at this definition and forget about it, because you'll probably never use it again. If you do plan to take 760, then it's good to try to understand this, and yeah, for better or for worse, you're going to get better understanding in the next homework assignment. I hope I don't cause too much heartburn as you get this better understanding. But so each coordinate of your random vector is a random variable, and the random vector is associated with a probability space in Rn and the set of Borel sets in Rn and the appropriate probability measure, most commonly a Lebesgue measure, which is another thing that we'll have to learn a bit if you're doing the PhD problems in the homework assignments. The Borel sets in Rn are defined very similar to the way they are in R, just a sigma field generated by the set of open sets in Rn. And by definition to be a random variable, that the inverse image of every Borel set has to be contained in omega, which, if you've forgotten this definition of a random variable already, this is the definition you have to remember. Might come in handy if you're doing the 690 problems on the next homework assignment. If you can't remember how to show that that thing is a random variable, well, that's how. Show that the inverse image of every Borel set is in the original omega. So, enough sigma fields for now. Let's go to something that is a little less painful to think about. Let's go to a simple coin tossing example. That say we flip a fair coin 3 times and we define a random vector xy. X is the number of heads on the last toss and y is the total number of heads. Well, hopefully it's fairly easy to calculate all possible outcomes for that when we toss a coin 3 times, obviously a total of 8 possible outcomes in the original outcome space. The first variable is x if the third toss is heads, and 0 if it's tails, and the second variable is just a count of the total number of heads. Each of these outcomes is equally likely with probability 1 over 8. Hopefully this is reasonably self-explanatory. I'll just note for the benefit of those who are doing the PhD problem that if it helps you wrap your brain around what does this random vector thing mean in the abstract sense, that the original outcome space is the set of sequences of heads and tails, and x and y is a function that takes one of these as an input and gives you a two-dimensional, a vector in R2, an x and a y as an output. So like I say, it's just a function from here to here. So say for instance, if we were going to try to show that x is a random variable, you would have to look at the inverse image of every possible Borel set, which is actually very easy to do here because x only takes on two possible values, 0 and 1. So the inverse image of every possible Borel set would just be the inverse image of basically set 0, 1, 0, 1, and the empty set, and just show that the inverse image of every one of those possible sets is contained in the original outcome space, if that makes the upcoming homework any less painful. But as I said, if you're a master's student, then you can probably just ignore what I just said. But we can define joint probability mass functions for random vectors just like the way we did for individual random variables, that if you want to find the probability that x equals little x, y equals little y, then that's just defined to be little f of x and y evaluated at x and y, just like in the case of an array of the single probability mass function. This has to be greater than 0 for every possible value of x and y, or greater than or equal to 0, I should say, and they have to sum up to 1. And given this joint probability mass function, if you want to find what we call the marginal probability mass functions, which means that like basically the probability mass function for x alone, or the probability mass function for y alone, the equivalent of the probability mass functions that we calculated for single random variables. You can do that by taking the joint probability mass function. To get the joint probability mass function, or marginal probability mass function for x, you just take the joint and sum over all possible values of y. To get the marginal for y, you just sum over all possible values of x. Hopefully that agrees with your intuition. If you're having trouble wrapping your brain around that, I'll give an example on the next slide that will hopefully make this clear. So this goes back to our fair coin example again, where we toss a fair coin 3 times, and x is the number of heads on the last toss, y is the total number of heads across 3 tosses. So we can calculate the joint, technically a PMF here, although some books use PDF and PMF interchangeably. Say like the probability that x equals 0 and y equals 0 is 1/8, because that only happens if you get tails 3 times. Similarly, the probability x equals 1 and y equals 1 is 1/8. That only happens if you get 2 tails followed by a head. The probability that x equals 0 and y equals 1 is 1/4, because that can happen in one of 2 ways. The last toss has to be a tails, but exactly one of the first 2 tosses has to be a heads. It's 2 out of 8 ways that can happen, so probability is 2 out of 8 or 1 out of 4. And if you want to find the marginal distribution of either x or y, you just either sum across rows or sum across columns. That if you want to find the marginal PMF for x, that is the probability that x equals 0, for instance, you just take 1/8 plus 1/4 plus 1/8, which is 1/2. Likewise, the probability x equals 1 is 1/2, which as it should be, because x is just the result of the final toss, which should be heads with probability 1/2. tails with probability 1/2, which is exactly what we expect. Similarly, if we want to find the marginal PMF for y, then we would sum columns. The probability y equals 0 is 1/8. Probability that y equals 1 is 1/4 plus 1/8, which is 3/8. Y equals 2 is 3/8, etc., etc. You may recognize that's just a binomial distribution with n equals 3 and p equals 1/2, which, again, it should be because we're just tossing a coin 3 times, counting the number of heads, which is the same sort of thing as we get for a binomial. It's exactly the same, so we would expect that to have a binomial distribution. So, in general, given a joint PMF, you can get the marginal PMFs, which are the PMFs for each variable individually, by just summing. And important to note that given that if you're given the joint PMF, you can easily calculate the marginal distributions by summing using the procedure I just described. It is impossible to go in the other direction. If you're given the marginal PMFs, you cannot calculate the joint PMF. In fact, I may give you a homework problem where you can show that for a given set of marginal PMFs, there's an infinite number of possible joint PMFs for those specific marginals. It's kind of a convoluted example, but the fact that this is possible at all illustrates that, in general, knowing the marginals tells you nothing about the joint. And similarly, that regardless of whether you have discrete or continuous random variables, you can define the joint CDF, joint cumulative distribution function, or joint CDF, and it's defined basically the way you would expect it to be for n equals 2, that big F of x and y is just the probability that x is less than or equal to x and y is less than or equal to y. Very similar to the way it was defined in the one-dimensional case. And properties of the CDF, once again, it's always greater than or equal to 0, as it better be since it's a probability. If you let both x and y go to infinity, it will be equal to 1. Again, because both x and y have to be less than or equal to infinity eventually, so this joint probability should go to 1 as they both get large. And if you let either of them, either x or y, go to minus infinity, that probability goes to 0 because eventually the probability that x is that small goes to 0, or the probability that y is that small is going to 0. And since this is defined as an AND statement, probability x less than or equal to x and y less than or equal to y, if x is going to 0, then this AND probability is also going to 0. And not surprisingly, if they both go to minus infinity, then that will give you a 0 as well. And just like a one-dimensional CDF, f is always non-decreasing with respect to both x and y, and it's also right continuous with respect to both x and y. And as I alluded to before, given big F of x and y, you can calculate the univariate CDFs for x and y, which we call the marginal CDFs once again. And to do that, the simplest way is given big F of x and y, if you want the marginal CDF of x, then you just let y go to infinity. Similarly, if you want the marginal CDF of y, you let x go to infinity. Again, hopefully that agrees with one's intuition, because you plug in infinity into the joint CDF, that gives you the probability x less than or equal to x, the probability that y is less than infinity. Well, the probability that y is less than infinity is 1, so that becomes just the probability that x is less than or equal to x, which is, by definition, the marginal CDF of x. So, given the joint CDF, we can calculate the marginals just by plugging in infinity for the variable, or variables that we don't care about. I mean, I don't show it in these slides, but the same thing works if you had a joint CDF of several different variables. And if you had a joint CDF of several different variables and you wanted to let them all go, and you wanted to find the marginal CDF of x1, you would just let x2, x3, up to xn all go to infinity. You're left with the marginal CDF of x1. Although, it's just I'm saying this, I'm trying to remember if I can think of a single multivariable distribution where the CDF has a nice form. I can't think of one, maybe one exists, but once again, although you can go from the joint CDF to the marginal CDFs, you cannot do the reverse. In fact, you can find examples where there are infinite number of possible joint CDFs given a set of marginal CDFs. And if you want, in any type of joint probability statements about x and y that you care about, you can write in terms of the joint CDF. For example, if you want to find the probability that x is greater than x and y is greater than y, then you might need to draw a picture or something to convince yourself of this. But if you do the math, you can show that that's going to be equal to 1 minus big F of x minus big F of big Y of y plus the joint CDF evaluated at x and y. This is similar to the inclusion-exclusion principle that we did for finding the probability of A union B, that if you subtract off big F of x, or big F of x and big F of y, you end up subtracting off the lower left-hand corner twice, so you have to add it back in. And more generally, if you want to try to find the probability that x and y are contained in some particular rectangle, you can calculate that by evaluating the joint CDF at x2, y2 plus x1, y1 minus x1, y2, x2, y1. But again, I won't go through all the details of this. It's just a bit of algebra. The easiest way to see it is to draw some pictures, or you can just take my word for it. Oh, now we'll discuss some continuous bivariate random variables. That most of the stuff we've discussed thus far is kind of focused on the discrete case. The continuous case is similar, although it gets a little bit messier because we have to deal with integrals and stuff. But random variables x and y are said to be jointly continuous, or sometimes jointly absolutely continuous, and as they say in some books, because once again, quick reminder for 690 students, you need absolute continuity to have the function be equal to the integral of its derivative, which among other things implies that a PDF exists. So you say that x and y are said to be jointly absolutely continuous if this PDF little f of x and y exists, such that for any Borel set in R2, the probability that x and y is an element of that Borel set is obtained by just taking the double integral over that particular set with respect to this density function. In this case, little f of x and y is called the joint probability density function, or the joint PDF for short. And it's easy to calculate the joint CDF from the joint PDF by taking the appropriate integrals, and like I said, at least in every example that I can think of off the top of my head of joint distributions that people care about, if you want to calculate the joint CDF, I mean, you have to integrate is the bottom line. In fact, I mean, I'm trying to think of how often in practice anybody ever uses the exact form of any joint distribution that's not the multivariate normal. It probably happens, but it's not common. Multivariate normal is far and away the most commonly used. And given the joint CDF, you can find the joint PDF by just taking the partial derivatives of the joint CDF. First take the partial with respect to x, then with respect to y. If it's been a while since you've taken multivariable calculus, the order that you take those partial derivatives doesn't matter. If it's an absolutely continuous function, you'll get the same answer either way. So properties of the bivariate PDF, like a univariate density function, it has to be greater than or equal to 0. It has to integrate to 1. If you integrate from minus infinity to infinity with respect to both variables, or more generally, if you integrate over the entire support of the distribution, it must integrate to 1. The support doesn't necessarily need to go from minus infinity to infinity, and if it doesn't, that integral is equivalent to just integrating over the entire support. And again, f of x and y is not a probability, but you can think of it as a relative probability that x and y falls into a small rectangle located at x and y. It's the same intuition as a univariate PDF that the PDF for a continuous random variable doesn't give you an exact probability, because the probability of observing any particular value of a continuous distribution is always 0. But it can tell you that you're more likely to observe x equals 0 than x equals 3, for instance. You can think of it as just kind of like a relative probability that x and y are located near the given x and y. And you can calculate marginal PDFs, kind of similar to what we did in the discrete case. As you'll recall, in the discrete case, to obtain the marginal PDFs, or the marginal PMFs, for x, we just summed over all possible values of y. Similarly, to obtain the marginal PDF of y, we sum over all possible values of x. Now we're in the continuous world, so we can't sum per se, but we do the continuous analog, which is just integration. That to get the marginal PDF of x, then you integrate with respect to y over the support of y. Similarly, to obtain the marginal PDF of y, you integrate with respect to x over the support of x. So, simple example of a joint CDF and how you would calculate the marginal CDFs and PDFs and so forth. Let's say that the joint CDF is x times y for both x and y in the area from 0 to 1. Well, to calculate the joint PDF, as I said before, all you do is take the partial with respect to x, then the partial with respect to y, or if you want to take the partial with respect to y first, it doesn't matter. You take the partial with respect to x, you get y. You take the partial with respect to y, you get 1. So the joint PDF here is equal to 1 in that rectangle and 0 everywhere else. If you don't recognize this, this is just saying that x and y are uniformly distributed in the square from 0, 1, where x are both between 0 and 1. This is basically the multivariate analog of the uniform distribution. So to find the marginal density of x, we integrate the joint density function, which is 1, from 0 to 1 with respect to y, and that, of course, is still 1. To get the marginal density of y, once again, we just integrate 1 from 0 to 1 with respect to x, and get 1 once again. Not very exciting, but again, it should agree with our intuition that if x and y are uniformly distributed on that square, both the x-coordinate and the y-coordinate should be uniformly distributed between 0 and 1, which is exactly what we observe here. So now let's try a slightly more convoluted example that the way these notes were originally written, they didn't write in like what these various joint and marginal PDF/CDFs were. They wanted me to ask the people in the class to calculate them. It took me an embarrassing long time to calculate it myself, so I decided not to inflict that on you. But yeah, if you ever struggle remembering how to take partial derivatives, you've got good company anyway. So to find the joint PDF of x and y, you just have to take the partial derivative with respect to x and the partial derivative with respect to y, which is easy if you remember how to do it, but some of us, unfortunately, takes us a few minutes to remember that, but I'll write it out so that you don't have to sit there feeling squeamish, not remembering how to take partials like I did, or maybe you all remember and I'm just the only idiot in this class, but anyway. So, the easiest way to do this, I found, was to take the partial with respect to y first, because then the x term at the beginning doesn't have y in it at all, it's constant, just goes to 0, and you end up just taking the partial of this piece here. All you have to do is use the chain rule. So minus x is a constant, so minus x times, first of all, the derivative of log x, which of course is 1 over x, so you just flip x over y to y over x, gives you that, times the derivative of the inside part with respect to y, which is x over y. So that derivative is minus x over y squared. You simplify all that out, you get x over y, then take that partial with respect to x, and you get 1 over y. So the fact that I got something that looks relatively nice reassured me that I did this correctly. Now, if you want to find the marginals, this time the joint PDF isn't equal to 1 everywhere, it's equal to 1 over y. So to find the marginals, you have to integrate the joint PDF with respect to y to get the marginal with respect to x, and this threw me for a loop when I was trying to do it just because the support of this distribution is weird. It doesn't go from 0 to 1 for both x and y. It only goes, as you see, it's only defined in the region where x is less than or equal to y. So to integrate over the entire support of y, you don't go from 0 to 1, you go from x to 1 because y is bounded below by x. You take that derivative and you get minus log x, which threw me for a loop for starters. Then I remembered that log x is negative for x between 0 and 1, so minus log x is positive, so that is a valid PDF, and I breathed a big sigh of relief. And similarly, to find the marginal distribution of y, you integrate from 0 to y, because x is bounded above by y in this case, of 1 over y. In this case, y is constant with respect to x. You can pull the 1 over y out of the integral. You end up integrating from 0 to y dx, which is of course equal to y, so y times 1 over y equals 1. The marginal distribution of y is exactly equal to 1 here, and yeah, really embarrassed to admit how long it took me to put this slide together, because the jerk who gave these slides to me didn't actually write the answers in the slides and thought that I would just remember how to do it, heaven forbid. So, given the joints, given the marginals, PDFs of f of x, and well, that's a typo, that should be f sub x of x and f sub y of y, not that it matters that much, but I'll try to remember to fix that. We can obtain the marginal CDFs directly, that to get the marginal CDF of x, this was like my sanity check to convince myself that I had in fact calculated this correctly. If we've done all this right, if we calculate the marginal CDFs and then differentiate them, we should obtain the same marginal PDFs that we got up there. So this is me checking that I actually did that right, plus just illustrating the fact that all this works. So given this joint density, given this joint CDF, how do we calculate the marginal CDF? Well, once again, you would plug in infinity for y, or in this case, we plug in 1, because 1 is the maximum possible value of y. So the marginal CDF with respect to x beats the joint CDF evaluated at x comma 1, which is of course equal to x minus x log x. If you differentiate that, you end up, and remember to do a chain rule, that didn't take me quite as long to remember how to do, you end up with minus log x, which is exactly what we ended up with up here, and I breathed a huge sigh of relief I didn't have to stand in front of class and admit that I don't remember how to do calculus. Similarly, to calculate the marginal CDF of y, and this is something that kind of really threw me for a loop, and there's a typo in this as well, but I kept trying to plug in 1 for x, and actually no, that's not a typo, because I kept on trying to plug in 1 for x and was getting something that made no sense and couldn't figure out what was going on. Then it occurred to me that I should not be plugging in 1 for x, because x is bounded above by y, so rather than plugging in x equals 1, I should be plugging in x equals y, because that's the largest possible value for x here. I do that, and I end up with log y over y, which is of course just log 1, which is equal to 0. I get that the marginal CDF of y is equal to y, differentiate that, and I get 1, so it does indeed all work out. But I always hate dealing with joint distributions where the support of one variable depends on the other variable, because you have to think about these limits of integration, and even in a relatively simple case like this one, it gave me a major headache while I was trying to put this together last night. So anyway, now conditional distributions and this idea of independence. That is, you'll recall, if A and B are two events, then we define the conditional probability of A given B, which intuition is the probability that A happens given that B has already happened. This is defined to be the probability of A and B over the probability of B, and well, that's nice. I remember seeing this typo on my slides last night and going into my LaTeX code to fix that typo, but it looks like I forgot to upload the fixed version onto Sakai. Awesome. Well, I will try to make sure that I upload the fixed version tonight once I fix the other typo that I noticed on the previous slide. So, Hmm?
What's the type of
It says P times A intersect B on the top rather than saying probability of A and B. I mean, not a huge typo, but it's kind of annoying. But, oh yeah, because I think what I must have done, I fixed it in my LaTeX code, then I didn't recompile the lecture slides, but I did successfully compile the handout. So the handout's right, but the slides are still wrong. This is probably a sign that I should put my slides together before 3 in the morning, but anyway. So if we define the event that A is y is equal to y and B is that x equals x, then the probability that y is equal to y and x is equal to x, of course, is the probability x equals x and y equals y, divided by the probability that x equals x, which, if these random variables are discrete, that, of course, is equal to just the joints PMF of x and y evaluated x comma y divided by the marginal PMF of x evaluated at x. And this is precisely how we define a conditional distribution, that you just take the joint PMF or PDF, divide it by the marginal, and then we call that the conditional PDF or PMF. So this is called the conditional probability mass function or the conditional probability function of y given x. So going back to the coin tossing example that we considered earlier, recall we toss a coin 3 times, x comma y is defined, x is the number of heads on the last toss, y is the total number of heads. So we saw the joint PMF earlier. We saw that if you want to calculate the marginal PMF for x or y, you just sum across rows or across columns. Now, if you want the conditional PMF with respect to x or y, the way you would calculate that is you take the joint inside the table and then divide by the row sums or the column sums. For example, if you want to find the probability that y equals 0, given that, or if you want to find the probability that x equals 0, given that y equals 0, that would be 1/8 divided by 1/8 equals 1. Again, agrees with our intuition. If we're given that the total number of heads is 0, then with probability 1, the last head has to be 0. Or if we're given that the total number of heads is 1, the probability that the last one is a head would be 1/4 divided by 3/8, and I'm not even going to embarrass myself by trying to divide fractions in front of my head in front of the classroom, but you get the idea. And similarly, that if f of x and y is absolutely continuous, you can get the conditional density of y given x by just taking the joint PDF divided by the marginal PDF if the marginal PDF is greater than 0. Otherwise, this conditional probability doesn't make sense because you're conditioning on an event that can't happen. And since y is continuous, we can't think of this in terms of probability because the probability of observing any particular y is always 0. So once again, you think of it as small dx dy, and we're just dividing the relative probabilities. Yeah. Oh, and it's denoted as f of x given y once again. And yeah, you can show that this satisfies the conditions of a density and that it integrates to 1 and so forth. I won't bore you with that, but you can trust me the math works, or I think it's in Cassell and Berger if you really want to see it. So let's go back to the two examples that we did earlier. One, the joint uniform distribution. As we saw earlier, the joint PDF and both of the marginal PDFs are equal to 1, indicating that any point in that square, in that unit square, is equally likely. So to find the conditional PDFs, you just take the joint PDF, which is 1 divided by a marginal PDF, which is also 1, so it's still 1. Not very exciting. But again, it agrees with our intuition that since it's equally likely to be any point in that unit square, if we know where y is, that doesn't tell us anything about where x is, because it's still equally likely to be anywhere in the interval 0 to 1, and etc., etc. And side note that we'll be discussing more later, when you get that the conditional densities are the same as the marginal densities, that means that x and y are independent. So again, should agree with our intuition when we were just looking at simple events without considering distributions. If the probability of A given that B equals the probability of A, then we would say that A and B are independent. In the more general case of distributions, if the conditional densities are the same as the marginal densities, that means that the two random variables are independent of one another. So the more convoluted example now, where the joint CDF is x minus x log x over y. As we saw a couple slides earlier, the marginal PDF is 1 over y, or the joint marginal PDF is 1 over y. The marginal PDF of x is minus log x. The marginal PDF of y is 1. So to calculate the conditional densities, we just take the joint density divided by the marginals. That the conditional density of x given y is the joint density, which is 1 over y, divided by the marginal density of y, which is equal to 1. So we have 1 over y divided by 1, which is 1 over y. The support of this particular conditional random variable goes from 0 to y, because once again, since y is given, the assumption here is that the value of y is known, so the support of this distribution only goes from 0 up to y. And similarly, to find the conditional distribution of y given x, we take the joint density divided by the marginal density with respect to x, and we end up with minus 1 over y log x. And the support, once again, here we're assuming that x is known, so the lower bound of this distribution is x. Y can be anywhere between x and 1. And so we see here that y is marginally uniform, that if we don't know anything about x, y is just uniform on 0 to 1, but given x, it's not uniform, and x is the other way around, that the marginal distribution of x is not uniform, it's minus log x, but if we know what y is, then it has density 1 over y from the interval 0 to y, which is precisely the density for uniform distribution on 0 to y. So y is marginally uniform but not conditionally, and x is conditionally uniform but not marginally. Any questions about any of this? Okay.